All right. So I think the equation in question is somewhere on the upper right, at least upper right corner. At least it was on the picture that Arvind had as his background. So I'm going to talk about differential privacy and that equation on the curtain in the digital futures. And now I cannot advance my slide. What is going on? All right. And so, you typically give an outline of the talk, but today I'm just going to say that I'm going to talk about differential privacy in approximately 20 questions. So plus minus 20, and I hope it'll become clear why I'm doing that. So what is the problem that differential privacy or the equation in question is trying to solve? It has to do with our desire to gain insights, to learn something, to have new knowledge, but also protect the privacy of the individuals that contribute their data that can be analyzed to generate that new knowledge. So for example, we want to learn from health data without revealing particular diseases or other health markers of individuals, or we want to learn from a survey or from a census where people fill out lots of questions, and there will be a gold mine to learn new things, but then there is this risk that either information leaks directly or inferences can be made about people that they don't want to have made. So why is this still a problem? Well, one aspect to this is that it's not enough to look at the data itself and decide whether that's risky to share or not. But we also have to take into account that there can be side information, so information that's not included in that particular survey, for example, but that can be taken together with a data set. And then once you put the two sources together, then you can infer more than looking at the data sets individually. So one attempt or first attempt to solve the problem of how we can learn from data without endangering the individual's privacy is to simply take away identifying information, like taking away your name or your person number in Sweden, and or you can replace the name with a pseudonym or the identifier with a pseudonym. So there is no direct link back to the person, the individual that contributed their data. And the problem with this approach is that, well, first of all, you have to trust whoever handles the data to do that correctly. And even then, due to this side information, there is a risk of re-identification or de-anonymization, so-called linkage attack. And I just listed two examples that you might have heard of that come up in any talk about privacy usually. So just very briefly, Netflix had this prize where they wanted people to do analysis of Netflix data, and they had taken away all identifying information. And then there were some researchers who took another data set from IMDb, and then they were able to, by putting these two data sets together, link like the Netflix data to the identity of the people in the IMDb database, and so re-identify the people and their watching history and how they rated the movies and so on. And another example is where they try to release health data and anonymize it by taking again identifiers away. And Latanya Sweeney found an attack where she put data sets together and then found that there is surprisingly little that is needed to narrow it down to very few people and thus identify people. So in her case, then she re-identified the data of some governor, and his health records were then revealed. And she found out that in the US, at least, your gender, your zip code, and your birth date are enough to identify most of the population. So it's not enough to take away the name or the phone number or the social security number, for example. So let's look at another attempt to preserve privacy while gaining new information by data analysis. So if we use just statistics, then there is also a danger of endangering or risking people's privacy. So for example, if you take an image and you add noise to it, then depending on how much noise you add, the image can become more or less recognizable. But if you do this by, do this to several images and add noise to several images, then you can average them and get closer to the original data or the original image again. So you have to be careful about what noise to add. Then another possibility would be to mediate the access. And for example, you would limit the queries that someone can ask to a data set to say, well, you can only ask about the sum of some element up to row X of our database. And if you happen to know where the individual is located in the database, then you can query the system and you can ask about, okay, so what's the sum of X up to the person that I'm interested in? And then you can ask, what's the sum of X up to the person that I'm interested minus 1, so the previous one. And then you can have a look at the difference, and then that tells you what is the value of that person. So that's a very obvious example that you can do, but the general idea is that if you can ask several questions, then comparing them lets you deduce something about your value of interest if you go about it in a clever way. And they came up with a law about this that says it's a fundamental law of information recovery that overly accurate estimates of too many statistics, that is not private, or that destroys privacy. So if you have too fine-grained accurate information and too much of it, then you can infer unintended things that lead to privacy violations. So if you have like the means and the median and so on, then you can already find out much more than if you only have one, or if you have the median or the mean value distorted by noise, then that's also already better than to have an accurate value for that. And so there are also some examples of reconstruction or recovery of data. And for example, they were able to find out whether someone's genome information was included in some data set because they had the aggregate statistics and accurate values for that. Or one can reconstruct missing values if one has subsets that one can compare.
Sonja, isn't this a problem then if we are not going to give the exact data?
Yeah,
right? That somehow
yeah. If we don't give
purpose.
the exact data, then we have a loss of accuracy, and we'll come to that in a little while. So another roundabout way to get at the third attempt is to look at the question of whether I should participate in some survey or some census or some study. And by participation, I mean contribute my data. And I can base this decision on whether my participation makes a difference in the result. And if there is a big difference just because I'm participating, then there is also a bigger risk of loss of privacy, because then there's a danger of inference and so learning something about me or identifying that this must be my response. And if there is no difference whether I participate or not, whether I contribute my data or not, then it's pointless. Then I don't have to participate, because my participation is of no value whatsoever in the analysis. We don't learn anything. But if the difference is small, then I might be able to contribute a little bit to the new knowledge at a very low risk to my privacy. So that may be okay, and we'll explore that in a bit. Not participating does not mean that we don't have any loss of privacy. That's a bit counterintuitive, but even if I don't participate, if some study comes up with new data, new insights, and finding some correlation. So, for example, that if you are a smoker, you have an increased risk of cancer. And you know, if you're in this age group from that region, then from that gender, then you might be more likely to develop this disease or become an alcoholic or whatever. So you can have these inferences from things that are already known, that are either observable, like if you see someone smoking, then by this study that found the correlation with cancer, then you can infer that they have an increased risk of cancer, for example. Or if you know the demographics of someone, and that is, you know, mentioned in that study and correlated with some effect, then you can infer that there is an increased probability of whatever that property is being true, because you know the demographics of that person. So not participating does not protect against privacy loss, but if we take that away and just focus on how big is the difference that participation makes, then we can get somewhere. So, so how do I decide whether I can participate? What's a good set of conditions that make it so that I feel like my privacy is preserved and I contribute to new knowledge in that study? In 1977, Dallenius formulated a privacy goal saying that anything about an individual that can be learned from the data set can also be learned without access to the data set. So there shouldn't be any difference on whether you participate or not. In other words, you can't learn anything new about me. But both more realistically and ideally, in another way, you can formulate it as that you would learn the same things if I'm replaced by another member of the population. So if instead of using my data, you just use another random member of the population and use their data, and you should learn approximately the same things. And an adversary who would like to find out whether this is your data or it's not your data, whether you were included or not included, should not be able to distinguish between a world where your data was included for getting the results and a world where it wasn't included. So what's differential privacy for? Well, it allows me to participate. It allows me to make this decision about participation, contributing my data. And it gives a privacy guarantee. And we'll get to more details of that later. It's also a way of quantifying privacy and quantifying the accuracy of results. And we talked about, you lose some privacy potentially, even if you don't participate. The differential privacy separates this. So it separates the risks of privacy loss from any new learnings of studies, even when you didn't participate, from the risk or the harm of learning something because you participated, and focuses on the latter. So what difference does it make if you participate? So what does differential privacy mean? So the English language definition, according to Cynthia's work, is the outcome of any analysis is essentially equally likely, independent of whether any individual joins or refrains from joining the dataset. So, so we have some real-world computation, some analysis of census data, or some analysis of our browsing behavior, and then there is an output. And my opt-out scenario is that the input would be without my data, and the analysis done, and output calculated. And the difference, in some sense of difference that I will get to, is at most epsilon. And you can instantiate epsilon with a value, and then use that to come up with a guarantee of privacy, and also to generate a mechanism that fulfills the requirement. And for that, we need to have this notion of adjacent data sets. So we have a smaller data set and a larger data set, and the only difference between them is that the larger one contains the data of just one more person. And so quite late now in the talk, you might be wondering about, when do I get to see the formula? What does it look like? And here we are finally. And so differential privacy means that, we can say that an algorithm or a privacy mechanism gives epsilon differential privacy if for all pairs of data sets, D1, D2, differing in the data of one person, so two adjacent data sets, and all events S, and there we mean subsets of image of S, of A of the algorithm. So that means the results of the algorithm and any subsets of the results. So so if we run the algorithm on dataset 1 and we run the algorithm on dataset 2, then they should differ only in this epsilon value, so the probabilities thereof. So how does this work? It works by adding noise in a mathematically rigorous way. And I mentioned before that you could perturb an image, and then if you're not careful, then several instances of perturbation can be used together, and then you can reconstruct the original. So we have to be very careful about doing that. And adding noise is not a new concept. This has been done for a long time. What's novel with differential privacy is that you do it in a rigorous way that allows you to then have actual guarantees and also some properties that are very useful that I'll get to next. So we still have this definition that the outcome of any analysis is essentially equally likely, independent of whether an individual joins or refrains from joining the data set. And another way of looking at this is that we limit the slope of plausible possible values. What I mean by that is if you have all the possible values, and then on the y-axis you have the probability thereof or the plausibility thereof, then the more narrow and peaky this distribution is, the more privacy loss you have, because you reduce the uncertainty of an adversary that wants to find out. So now we have this result. How likely is it that it was generated from you, or it has? We have this this particular result, and how likely is it that that's actually accurate? And for an attacker to distinguish between true and noisy outcomes, we want to, or the attacker has an easier time distinguishing these if there are fewer plausible possibilities. And so instead of having this spiky distribution where there's a very narrow range of what the truth is that the attacker can choose from, we would like to even out the probability distribution and make many values approximately equally likely. Then how much noise we need to add, that depends on the sensitivity of the data, and that in turn depends on how many individuals contributed to the data. So what's the relative contribution of each person's data and other aspects of the data. So the more sensitive the data is, the more noise we need to add. But then we come back to Arvid's concern about, well, what happens if you add noise? Then your accuracy goes down. So here we have a trade-off between, how accurate is the result that we can publish, and how good is the privacy preservation. And it's not a linear trade-off, but in general we can say the more accurate, the less noise, the greater the privacy loss. And we try to find some sweet spot where the loss of accuracy and the loss of privacy are acceptable. And practically, how differential privacy works is by using Laplacian noise. So you have this Laplace distribution, goes up and down like this, and then you can vary, how wide the noise spreads out, and the wider it spreads out, the harder it is for an adversary to distinguish between the different worlds. So the world where my data is included and the world where it isn't included, and all the other data sets that just differ by one, because then you have overlaps of these distributions. So what do we get with differential privacy? So one of the main properties that we get is that it's future-proof. So remember when I talked about this issue of side information, that if you take another source and put it together, then you can get new inferences that you didn't have before. And here, this doesn't work. So there is no change in whether you have current or even future side information, or even if you process the outcome in any way afterwards. That does not change anything about the privacy. Another property we get is that it's not just individual privacy, but you can also quantify group privacy. And so instead of just taking epsilon value for an individual, if you want to protect groups of some size, then you have to scale epsilon according to the group size. But this is known and understood, and you can do this. And that leads to the next property, which is that we can understand composition. We know what happens if we compose differentially private mechanisms. So then you can make decisions about what to publish. And the colloquial term is that epsilon adds up. So if you decide to both publish the average and the median of some data set, and each with epsilon 3 in this example, then it just adds up that that would result in epsilon is 6. And then you can make a decision, okay, maybe that's too high and I don't want to go that high. So then I decide to only publish one and not the other, for example. And another interesting property we get is that, and that's also related, but slightly different, is that it's programmable. So you can build quite complex differential privacy mechanisms out from very simple building blocks. So just like in programming, where you can have very simple functions down to like and or, and then build subroutines and routines and whole programs on that. So another question is, how much privacy do we need? And I alluded to this trade-off between accuracy and privacy, or it's also sometimes called utility and privacy. And accuracy is more about how close is the published data to the real or the original data. So we have to weigh the benefits of new knowledge versus the drawback of privacy loss. And that's not so easy to do. And it's also not so easy to get an intuition of what does it mean to have an epsilon of X or Y. So the original authors of the 2006 paper said that, well, you should choose epsilon between 0.1 and 1. And then others found that, well, we will need to increase epsilon, otherwise we don't get enough accuracy and so on. So these are very difficult things to translate between human valuation of how much is it worth to me or to society to get this knowledge versus what is the harm of this much of privacy loss, again on an individual and on a society basis. So how can we measure privacy? And so I talked about this indistinguishability and adversaries trying to guess what's the most likely true value. So how many true possibilities are there? And if there is lots, then it's hard for an adversary to pick the right one. If there are only few, then you have this peak in the distribution, then it's much easier for an adversary to pinpoint what the true data is more closely. So you can measure this prominence in the peaks and like how steep they are. And how can we measure accuracy? So with differential privacy, you get results that are like 98% are within the range of plus minus 2 of the value 50, for example. And so you can regulate the parameters by saying that, so how close are you to the original or accurate value by, plus minus, giving the range. And also how likely are you to be that close to the original accurate value. So how many fall within that range. So there are cases when differential privacy is more suitable and works better than others. And differential privacy works best when there is a large data set and there is lower sensitivity, and meaning that the contribution of each individual person's data is quite small. So you have, if you have a million people and each contribute their data, then the contribution of each individual is very small in these relative terms, but also if the difference in the results doesn't change much in the computation, or the result of the computation doesn't differ very much whether included or not, then differential privacy works well and works better because there's less need to add noise. So you still will have to add some noise, but it can be small if you have a large data set and low sensitivity. And for type of queries, like number of types are more suitable. So you can ask questions like, how many people have this and that property? And that is a better type of question for differential privacy than if you have what's the maximum or what's the minimum or what's the sum of all the values, for example. Because then if you have data that is a bit of an outlier, then that can be possibly be inferred if your data is included. It can be inferred that it is your data. And similarly, or conversely, if you have a smaller data set and you have higher sensitivity and each individual person's data contributes more to the result relatively, then you need more noise. And then when you have more noise, then your accuracy goes down. So the privacy that you buy comes at a higher price if you have a smaller data set and higher sensitivity. Also, if you have these max, min, or sum queries. So where is differential privacy used? The US Census in 2020 used it for the first time. And they used it in the sense that they published tables of statistical data, and those tables are the results of the queries. So in this way, they were able to control how much of this epsilon is used for a particular query, and then also for all of the queries together. So you will also, if you hear about the budget of differential privacy, this is what is meant by that. So you have an epsilon and you can spend it on either, publishing one value and using up all the epsilon you have on that value to get it as accurate as can be, or you can release X values and then you use 1/x of the epsilon for each value. And you can do this in terms of tables as well. So the epsilon budget, the privacy budget is used up, but then there is no more information that you can gain than is already in those tables. So even with auxiliary side information, that doesn't help you. Then Apple and Google and Uber all have some analyses going on where they use differential privacy with varying values of epsilon, and mostly higher values than was originally recommended. And then there are a few others, but there are also few others. So you'd think that, well, here is a means to protect individuals' privacy and still gain new knowledge from data analysis, but it has not been widely adopted. So why is that? So why isn't everyone using it? So there are some problems that remain, and one of them is that it's difficult to communicate. So it's very difficult to get a feel for what does it mean to have epsilon of 2? What does it mean that the census is using differential privacy, and what's the real and perceived risk for me to participate? Then another problem is that you can run out of the budget. So so in the census example that I named, they reified the queries in tables, and those you can look at and do post-processing on as much as you like, and this will not diminish the privacy. But another way of using differential privacy is that you are allowed only as many queries of particular types until that privacy budget is used up. And then you can't query anymore. And then if you think about collusion, so maybe you give a budget to this researcher to analyze your data, and then you also give the budget to that researcher, then they can collude and exchange their responses with each other, and then avoid asking the same question of the data, and thereby circumvent the budget. So even if you have if you can do that individually, then that's there's this risk of collusion, but then you could also have an epsilon that's global. But then if these queries are asked, then what do you do? And one joke is that, well, then you have to kill the person doing the queries, because they know too much. But obviously this is not a good solution. Another obstacle is that compared to other attempts like de-identification or anonymization or pseudonymization, it's quite complicated to implement differential privacy and to do that correctly. And it's also interesting that people in computer science have been quite enthusiastic about differential privacy and accepting of it. And apparently statisticians are more reluctant to use differential privacy. And one of the reasons apparently is that it changes the way statisticians work. So they can no longer use the first step of, okay, let's look at the data and get an intuition for it. I mean, they can't do that with big data anyhow, but still it's a different process than what people were used to doing when looking at results of smaller scale, like maybe a few hundreds or so. But now you can't look at the original data that way, because then the cat is out of the bag. Another obstacle is that if you really use differential privacy with a small value of epsilon, then you have to add quite a bit of noise, which reduces the accuracy. And then if the accuracy is reduced so much that you don't get much utility out of the analysis, then that's not good. So you want to have something that gives you higher accuracy. Now, whether that's possible while also protecting the privacy is another question, but it's certainly an obstacle. And you also need to trust the data curator or the data processor to do it correctly. So to have overcome this complication and have understood the composition and implement it correctly. And, on top of having all the security measures in place that prevent people from just accessing the original data. So there are some obstacles still on the way to adopting differential privacy. So why do we even care about this? And one answer to this is that we're damned if we do and damned if we don't. And by that, I mean that if we only have data analysis that doesn't preserve privacy enough, then we get all the harms from privacy violations. And they can be that people are being discriminated against because of some property they have. Maybe they need to pay higher insurance. Maybe they're barred from something. Maybe the AI decides that, no, we cannot grant you this request because you have this pre-existing condition or whatever. Or people can get exploited. Social engineering works better if you know information that people usually keep private that can be used. And there's a loss of control over what data is disclosed to whom, what inferences are made about you, what consequences your behavior have, and so on. And in extreme cases, you can also be persecuted for your private political opinions or sexual orientation or whatever, if that can be inferred from your data, if you lose that privacy. On the other hand, if we don't analyze data, if we can't learn from data that is withheld because there are privacy concerns. So we need to find ways of hitting this sweet spot with accuracy and privacy that is acceptable, so that we have enough accuracy to get useful results, but also enough privacy to not endanger individuals and have them suffer from the harms I mentioned. And then there are, of course, many more. So what now? What can we do now? So one avenue is to work on the remaining problems of differential privacy. And there are, for example, there are different notions of privacy that are more adapted to different scenarios in a way, in an attempt to increase the accuracy at not much loss of privacy. So find a better spot on that trade-off, or maybe find a better trade-off overall. Then one can also look at other alternatives, and some of them may work in some scenarios, and some have, different scenarios from the typical use case of differential privacy. But you can look at cryptography, for example, and multi-party computation, or fully homomorphic encryption, where you can perform computations on encrypted data. Now, these have a performance problem still now, but there have also been lots of advances, and especially in some more like narrowed cases. And you can look at, for example, to use synthetic data, but then again, there are also risks depending on what you use them for and how you do that. Another way can be to combine differential privacy with other approaches. And for example, there are hybrid approaches between differential privacy and k-anonymity, or you might have heard of federated learning, and using differential privacy to make machine learning more privacy preserving. So there are lots of research avenues in building on differential privacy, and using it in different ways and trying to improve it and solve the remaining problems. So at the end, one always wants to know who done it. So who has committed this? And I just list the authors of this 2006 paper, because they were the ones that formalized epsilon differential privacy. So different notions of privacy that used randomized results and adding noise have been used for a long time, but this is the first that actually gives a guarantee and quantifies the effect. So, and time is running out, and yeah, thank you for your attention, and I'd be happy to answer any questions if there are more than the 20 I posed today.